Have you ever wondered why businesses don't connect computers directly with network cables? What makes a network switch so important? And why can two computers connected to the same switch still fail to communicate? Today we're going to answer both of those questions. In our previous lesson, we built our very first network by connecting two laptops directly using a crossover cable. We configured IPv4 addresses, learned how the network ID and subnet mask work together, and verified communication using the ping command. Let's start where we left off. Right now, our network consists of only two directly connected laptops. Now let's imagine our network begins to grow. Another laptop needs access to the network. Then another computer is added, and finally, a shared network printer. As more devices are introduced, connecting every device directly to every other device quickly becomes impractical. Instead, we introduce a Layer 2 Ethernet switch. A switch becomes the central connection point for every device on the local network. Instead of devices communicating through dedicated cables, every computer connects to the switch. The switch then forwards network traffic only to the device that should receive it. This makes the network easier to expand, easier to manage, and much more efficient. In this lesson, we'll replace our direct connection with a Layer 2 switch, reconnect our original laptops, verify that communication still works, and then discover why two computers connected to the same switch still can't communicate when they're configured on different IP networks. Let's get started. Before we begin connecting our devices, let's give our switch a meaningful name. By default, Packet Tracer assigns a generic device name. We'll change that so it's easier to identify as our network grows. Select the switch, then open the Config tab. Under Display Name, replace the default name with SW-01. This changes the label you see in the workspace, making the topology easier to read. Now let's also change the switch's host name. Click the CLI tab. When prompted, press Enter. At the prompt, type Enable and press Enter. Next, type Configure Terminal and press Enter. Finally, type hostname SW-01 and press Enter. Notice that the command prompt now displays SW-01 instead of the default hostname. The display name helps organize the topology visually, while the hostname identifies the device from the command line. In a real network, it's common practice for both names to match. Now we're ready to reconnect our devices. Instead of using the crossover cable from the previous lesson, we'll use copper straight-through cables. Why? Because we're now connecting end devices to a network switch. A crossover cable is typically used when connecting similar devices directly together, such as one computer to another. A straight-through cable is used when connecting different types of devices, such as a computer to a switch. We'll explore Ethernet cable types in greater detail in a future lesson. For now, simply remember this rule. Computer to switch, use a straight-through cable. Select the copper straight-through cable. Connect laptop 01 Fast Ethernet 0 to SW01 Fast Ethernet 0/1. Next, connect laptop 02 Fast Ethernet 0 to SW01 Fast Ethernet 0/2. You'll notice that the link lights remain amber for a few moments while the switch initializes the ports. After a few seconds, they'll turn green, indicating that the links are operational. Now let's verify that communication still works. Open the command prompt on laptop 01. Type ping 192.168.1.20 and press Enter. The first ping may time out. That's completely normal. When devices communicate for the first time, they first need to learn each other's MAC addresses using the Address Resolution Protocol, or ARP. Once that process completes, the remaining ping replies should succeed. Although we've changed the physical topology, our IP addresses haven't changed. Both laptops are still members of the same 192.168.1.0/24 network, so communication continues to work exactly as before. Now that our switch is in place, let's see what happens when we introduce a computer that's configured on a completely different IP network. Now let's add another computer to our network. From the End Devices menu, drag a PC onto the workspace. We'll rename it PC-01. Select the new PC. Open the Config tab. Under Display Name, replace the default name with PC-01. Next, select the Fast Ethernet 0 interface on the left panel. This is the PC's network interface, sometimes referred to as its network port. In the IPv4 address field, enter 192.168.2.10. Now click inside the subnet mask field. Packet Tracer automatically fills in the value 255.255.255.0. This subnet mask is also written as /24. A /24 means that the first 24 bits identify the network, while the remaining 8 bits identify individual devices or hosts within that network. Because of this, 192.168.2.10 belongs to a different network than our two laptops. Even though the subnet mask is the same, the network address is different. Now connect PC-01 Fast Ethernet 0 to SW-01 Fast Ethernet 0/3 using another copper straight-through cable. Wait a few seconds until the link light turns green. At this point, all three devices are physically connected to the same switch. So let's test communication. Open the command prompt on PC-01. Type ping 192.168.1.10, which is the IP address of laptop 01, and press enter. Notice that every packet times out. The ping fails. At first glance, that might seem confusing. After all, everything is connected to the same switch, but this demonstrates one of the most important concepts in networking. A switch forwards Ethernet frames. It does not route traffic between different IP networks. Our two laptops belong to the 192.168.1.0/24 network. PC-01 belongs to the 192.168.2.0/24 network. Those are two completely different networks. Without a router or another layer 3 switch device, there's nothing available to move traffic from one network to the other. So even though every device is connected to the same switch, PC-01 cannot communicate with either laptop. Let's prove that the problem isn't the switch. We've just seen that PC-01 cannot communicate with either laptop. But does that mean the switch isn't working? Not at all. Let's prove it. We'll add one more computer to the network. From the End Devices menu, drag another PC onto the workspace, rename it PC-02, open the Config tab, and change the display name to PC-02. Next, select the Fast Ethernet 0 interface. Assign the IPv4 address 192.168.2.20. Click inside the subnet mask field, allowing Packet Tracer to automatically populate the value 255.255.255.0. Notice that PC-02 uses the same subnet mask as PC-01, and more importantly, both devices belong to the 192.168.2.0/24 network. Now connect PC-02 Fast Ethernet 0 to SW-01 Fast Ethernet 0/4 using another copper straight-through cable. Wait for the link indicator to turn green. Now let's test communication again. Open the command prompt on PC-01. Type ping 192.168.2.20 and press enter. Just like before, the first ping may time out while the devices exchange ARP information. After that, the remaining replies should be successful. This tells us something very important. The switch has been working correctly all along. PC-01 and PC-02 communicate successfully because they belong to the same IP network. Earlier, PC01 couldn't communicate with Laptop 01 because they belonged to different IP networks. The switch didn't block the communication, it simply forwarded Ethernet frames within the local network. Understanding this difference is one of the most important building blocks in networking. The switch provides local connectivity. IP addressing determines which devices belong to the same network, and routing is what allows different networks to communicate with each other. Let's review what we've accomplished today. We began by replacing a direct cable connection with a Layer 2 Ethernet switch. Instead of connecting devices directly to one another, every device now connects to a central switching device. This makes the network easier to organize, easier to expand, and much easier to manage. Next, we verified that our original laptops could still communicate successfully. Changing the physical topology didn't change the IP network. Both laptops remain members of the 192.168.1.0/24 network. Then we introduced PC-01, configured with an address in the 192.168.2.0/24 network. Even though it was connected to the same switch, communication with the laptops failed. Finally, we added PC-02, configured within the same 192.168.2.0/24 network as PC-01. This time, communication succeeded successfully because both devices belong to the same IP network. Today's demonstration highlights an important networking principle. A switch provides Layer 2 connectivity, but IP addressing determines which devices can communicate directly. Remember these three key takeaways from today's lesson. First, a Layer 2 switch connects devices within the same local network. Second, devices must belong to the same IP network to communicate directly through a Layer 2 switch. And third, communication between different IP networks requires Layer 3 routing. These concepts form the foundation of nearly every enterprise network you'll encounter. But here's an interesting question. If a switch can connect hundreds of devices, should every computer belong to the same network? In a real business environment, the answer is no. Different departments, such as sales, human resources, finance, and IT, are usually separated into their own logical networks for better performance, security, and management. In the next episode, we'll introduce virtual LANs, also known as VLANs, and discover how a single switch can create multiple isolated networks without adding additional hardware. I'll see you in episode 3.